What do we mean when we use the terms parallel and concurrent? What's the difference? And how are they related? Hi, my name is Eric Normand, and these are my thoughts on functional programming. So, in the recent episode, I talked about race conditions and the conditions under which you would get a race condition. So you have two threads or two timelines that are sharing a resource. And it's that sharing of the resource that makes something, it could be problematic, you could have a race condition, or it could be a thing about concurrency. Okay, so concurrency is all about sharing resources. Resources could be anything. They could be a global variable, it could be a database, it could be a network connection, it could be the screen that you're printing out in your terminal. All of these things are shared resources among different threads. Concurrency is all about efficiently and safely sharing those resources. That's what it's about. Your resources, you could also say your CPU is a resource, right? So you can have a task scheduler that allows you to share that one CPU among different processes. That's one way to look at it, but it's all about sharing these resources. Parallelism is about increasing the number of things that are sharing the resources. Okay, so that's increasing the number of threads. That's increasing the number of nodes in a distributed system. So this is making something more parallel. Now notice it's very hard to make things parallel if they're not sharing safely and efficiently, right? So they are intertwined. This idea of concurrency, how we share things, and parallelism, which is how many things are sharing the thing. How many things, and also how, you could look at it in another way, which is if it's a CPU. That's why the CPU one is a little hard, because it's the thing that's being shared and it's the thing that things are running on. But you could look at it like you are increasing the number of CPUs, right? So that increases the number of threads that actually can run at the same time and not have to switch out to run, because you can start actually having multitasking. So you're increasing the number of things that are shared, but also the number of things that are running at the same time. Okay, so it gets a little, like it's a big corner case when you're sharing the CPU, because that's also what you're running on. But the main point is that concurrency is about sharing resources safely and efficiently. Safely meaning without race conditions, or without bad race conditions that could lead to the wrong result. And parallelism is about, once you have that, being able to increase the number of things that are sharing. Different concurrency mechanisms exist. Okay, concurrency mechanisms, you can think of them like most of them have parallels in the real world. Okay, so a simple example is if you want to share a bathroom with people. So you have 6 people living in the house. There's one bathroom. How do you share that safely and efficiently? Well, you could put a lock on the door. So that keeps other people out while one person is using it. So that's kind of the safety, right? It's still private, and it's pretty efficient because you can tell the door is unlocked. You can go in and just, use the bathroom, and then you unlock it on the way out. It's pretty clear what the rules are. But imagine if you had something like 12 or 18 or 25 people in that house. Maybe a lock is not going to work anymore. maybe you're going to start seeing, for instance, someone who's had to go to the bathroom for 2 hours and they just keep missing their turn. You're probably going to want something more robust to ensure that everyone can share that, right? It's not just the fastest people can get to the bathroom. So another mechanism we use all the time is a queue. So lining up. You want to order food at the restaurant. You get in line, and they're processed in order. The order you get in the line, and so that means everyone has a fair chance, right? That resource, the person who's taking orders, is going to be calling people up one at a time, and it's fair. We intuit that it's a fair system. And this is a concurrency mechanism that's used all the time. Another one is something like a schedule, right? So instead of getting in line, you could put your name on a list. I know restaurants are doing this now in my city, where you go up and you put your name on a list, and when the table is available, they'll text you, right? So that means it's async. It's asynchronous. That means I can go, take a walk while my table is being used, and then once it's free, I'm notified, and then I can go back. So I don't have to just wait in line, right? It's a little bit more efficient. And it probably lets you handle more people, I imagine. Especially since if it's going to be 2 hours before I can sit down, I'll probably go home, right? And come back later when it's closer to the time that they're estimating. So these are all concurrency mechanisms that you can find in a computer. So in the first case, a lock, there's a thing called a lock in programming. It's also called mutual exclusion or a semaphore. It's a way of making sure that only one thread is accessing the code, that block of code at the same time. There's queues. So there's multiple implementations of queues where you put a value in the queue that signals the work that you want done. And then when the CPU is available to do that work, it will pull the next thing off of the queue and just process them one at a time. And there's schedules or callbacks, things like that, like you have with the texting when my table is ready. And so these concurrency primitives are really important, and I think they're something that we in functional programming, because I have to say, I'm not the only one who believes this, but concurrent programming, distributed systems programming, parallel programming is really the killer app for functional programming. People were talking about having, hundreds, thousands of cores on our machines, and so we'd have to start programming those. That didn't really happen, but what did happen was we're now programming distributed systems all the time. So your cell phone has an app, and that app is talking to the server is talking to the database, talking to 3 third-party APIs. It's all distributed now. I mean, not every piece of software is distributed, but most of them are distributed. And functional programming does really well with this because you can have distributed concurrency constructs. I won't go into those right now. So that's why I bring up concurrency and parallelism, because that's really what functional programming does best. It uses immutable values, which are able to be shared between different threads with no problems, no race conditions. If they're immutable, it means they never change, which means any copy I have, you can share the same copy because it's never going to change. So what's the problem? We can both read it My thread can read it, your thread can read it, and it's totally safe. The problem comes when you can modify it, and then you start to get into, well, if you're modifying it while I'm reading it, what's going to happen, that kind of thing. So, that's parallelism and concurrency, and that's pretty much all I have to say on it. If you want to get in touch with me, if you have a question, or you want to disagree with me, or give me some praise, or tell me I'm wrong, you can email me at eric@lispcast.com. You can also find me on Twitter. I'm at Eric Normand with a D. And also you can find me on LinkedIn and, connect there. Don't forget to hit subscribe, and I'll see you later.